Okay. Okay, now let's, yeah, that's better, because the video for some reason is taking too much bandwidth. I don't know how exactly this works. Should be good. But I always want you to see me, that I'm a real person. You know that I'm the real person, especially when you're taking an online class. It's nice to see the instructor, because everything is online. You have to really navigate, but it's nice to have this eye contact a little bit. Okay, that's me. Let's see. That's enough of all of the announcement, but make sure that you have an appointment on Examity, okay? Because I don't know, hopefully everybody will read 5 minutes before meet them, because it's not letting, it's the proctor. Okay, emails on Monday, I will tell you that's what we have in chapter 4, derivatives, local maximum, revenue, and profit. And I do have, right? Probably not. Okay, let's try now. Yes, I can change now. That means I just took the information from your textbook, the definition of the local minimum and local maximum. What we have to do, we have to find a critical points. That means in order to find a critical point, we have to find the derivative and say derivative is 0. Because we remember, when derivative is 0, we have horizontal tangent. That means that's, for example, important point. We call critical point. Also, we have to identify the points, the x values, where derivative is undefined. Okay? Where derivative is undefined, let me, because I have to switch off this. You probably remember, or maybe we know that one of the nice function to indicate this is absolute value of x, like everybody remembers the v function. And we can see when we have these sharp corners, it's also important point. We know it's like a lowest point, probably is the local minimum value, but derivative is undefined at that 0. That means it's important to also find a numbers, values of x, that derivative is undefined. And then we can investigate. That means 0 and undefined are giving me critical points. And of course, critical points, they have to be in the domain of the function. Okay, that's one thing. And then having the critical points, we can check how derivatives behaves on one side and the other side of the critical point. Like, let's even look at this absolute value. We can see function is decreasing, then derivative is negative. Derivative is negative on the left-hand side, and on the right-hand side, function is increasing, derivative is positive. That means changing from negative to positive, from decreasing to increasing, we're creating like a locally lowest point. Okay? That means that's the way to check local maximum and minimum. But we will try to do this. Okay, then, oh yeah, we do have this. And we call this, what I just said, we call a first derivative test. So in having a critical point, P in this case, we have to test the sign of the derivative. Because we may have a situation that we do have a critical point, but derivative, unfortunately, is not changing the sign. Like, let's say it's decreasing. I can maybe write here, is decreasing and again decreasing. Yeah, we may have function like that. At the point P, we're gonna have horizontal tangent because derivative is 0, but function is decreasing. And this means that we have no local extreme values at that point. That's because one of the questions on the discussion board was, oh, I have my critical points, but the textbook is telling me that no maximum and no minimum at this critical points. And probably it's correct because we have to test the sign. Okay. Second derivative involves the concavity. We remember if the function is bounded up, which we will call concave up. Oh, hang on. That's because that's the second derivative test. That's okay. That's a little bit different. Second derivative test is also detecting local maximum or minimum. We may use, let me come back, we may use the first derivative test to determine maximum minimum or the second derivative. That means for the second derivative, we're using the second derivative test, especially if it's easy to compute the second derivative. That means what we can do, having a critical point, P, okay, that means having all of the solutions of this equation, we can try to compute second derivative and compute the value P. This means we do have bottom of that and negative number, then cave down, it's bended as a local maximum. That means this will be local maximum working. Really, because my audio is definitely good. Oh, you can see my pointer. I was pointing and I was even. Okay, let me, hang on, it's asking me, did I open? No, I can't open this. I'm just trying to close everything what I have on my laptop. No, it's okay. Oh, how can I come back to my... Okay, let's do this way. Okay. Hopefully now will be okay. Okay, that means first derivative or the second derivative test. Let's keep working because we have lots of questions today. And then inflection points. How can we find the inflection points? Inflection point is the point where the function is changing the shape from being bended up to bended down, which sometimes is not, when we're looking at the graph, it's not easy to to see. You may even notice now on the blue curve, because I can maybe say, oh, this is the moment, right? Like a little bit above. That we really have to find the point solving this equation. Second derivative is 0 at this point, but we also have to be really careful. Even if the second derivative is 0 at a certain point, we have to check the sign. Positive, sign of the second derivative, positive, negative. Right? That means make sure that the second derivative is changing the sign, because we may have a situation that the second derivative is not changing the sign. Like for example, let's say function is concave down and then concave down. Yeah, we may have function like that. We even know the formula for this. That means concave down, concave down. At this point, probably second derivative is undefined, which are also important points, like for the critical points. But we have to be careful. Second derivative must change the sign. Then we will know that this is the moment that the function is changing the shape. Okay? That means that's the possible inflection points. Or second derivative, it's the same like for the critical numbers, it's undefined, does not exist. That we have to find the values that second derivative is 0 or second derivative is undefined. And I can show you how we can do it. And we also, we call special numbers, but that's the just candidates for the inflection points. And then we have to test it. Okay? And then, yeah, that's actually another example that the second derivative is 0 here. We can see it's like flat, but it's not intersecting, it's not changing the concavity. Yeah? That means we do have second derivative 0, but we don't have inflection points. Okay. Also, in section 4.3, we talked about the global maximum and minimum. Global maximum minimum means that we have to detect the highest point on the curve and the lowest point on the curve, or the highest value, the maximum value of the function, or the minimum value of the function. Okay? Because we know what local means. Local means that locally this is the highest point, right? Locally this is the highest point. Okay? But let's say this local maximum, this one, is not really the highest point on the graph. The highest point on the graph is this one. That means this is, of course, locally the highest, but also absolutely highest, global maximum. And now, which one is the lowest? This one is the lowest. It is locally the lowest point, okay? But also is the lowest point on the graph, absolutely lowest, global minimum. Okay? And for example, looking at this function is going up without the bounds. That means we have no global maximum. We can't detect a finite number. But I can see my lowest point. My lowest point is this one, absolute minimum or global minimum. And of course, every single like a summit, I can say, summit, the top of the hill or the bottom of the valley will give me local maximum or minimum respectively. Okay, as we know what's the difference between locally highest point and the globally highest and lowest too. Okay. And how can we like find the global maximum minimum? We have to look at the domain and we have to look at all of the local values, all of the values at the end points, because we can see maybe the end point will give me the highest point. That's why I have to find everything. I have to try to find the values at the end points because we can see that's the end point. Okay, that's why I have to find the values at the end points, values for all of the local extreme, and the highest will be the global maximum, the lowest will be the global minimum. As simple as it is. The same for this one. This one, we don't have the endpoints. Yeah, that means that's sometimes the problem. We have to like know if we can detect the highest or the lowest point. Okay? But also local extreme values are involved in finding the global maximum minimum. But always the highest and the lowest point. Okay, that's now let's try to solve some problems. That was a little bit, yes, we go through the theoretical part. That's what I have. I did include a few slides with the questions from the discussion board, okay? Because you asked the questions and I will try to answer. That means one of the questions, this is section 4.1, and I think the questions 17 and 19. That means let's try to solve this one. For this question, we have to find critical points and use the first derivative test to determine local maxima and minima. And we don't have to graph. Maybe we can graph, but we don't have to. Okay, that means number 17. We have function x squared minus 4 to the power of 7. We know that in order to find the critical points, we have to set up derivative. First of all, we have to have derivative. But before I start, I will say that the domain of these functions are all of the numbers. Because we can see we don't have denominators, that means I don't have to exclude any numbers, and no even roots, because even roots takes only positive numbers. Okay, let's find the derivative. Quantity to the power of 7, which means derivative will be 7 times the same quantity to the power of 6, and follow the chain rule times derivative of the inner function, 2x. Right, we remember this. Let me rewrite nicely. 7 times 2, 14x, and then x squared minus 4 to the power of 6. Excellent. Now for the critical numbers, derivative is 0. If and only if 14x, and maybe I can rewrite x squared minus 4 as a x minus 2x plus 2, both of them to the power of 6. Okay, that's my derivative. We can see derivative is defined everywhere, right? That means I will not have the values that derivative is undefined. Okay, and now I can see zero product property. For this expression to be 0, x must be 0, x must be 2, or x must be negative 2. 0, 2, and negative 2. That means that's my critical numbers. Let's use that symbol. Okay, and we have to, that's what I said, we have to be really careful. I can't assume that for all of them, I will have local extreme values. No, we have to test it. That's me. Now let's test. That's x, and I will test, I can possibly use different color. I will test a first derivative. That means first derivative, let's say this is the good form. I am testing, because this is my first derivative. I'm testing the sign of the first derivative on the left and the right hand side of each number, each critical number. -2, +2, and 0. That's what we have to do. We simply have to take like a test value from each interval. You can pick any number. That's if I will put 3. If I'm substituting 3, 3, and 3, of course, we don't have to get the exact point, right? I'm not gonna like have 3 + 2, 5, 5 to the power of 6. No, no, no. But what I'm looking for the sign only. That means substituting 3 + 2 is positive. 3 - 2 positive. 14 times 3 positive, and of course to the power of 6. That means this will give me, this interval will be always positive. The derivative is always positive. Okay, no, I can keep that 3, but now I will test the second. I will test the second interval. Let's take the value between 0 and 2. Let's take 1. That means substituting instead of x 1. 14 times 1 positive. 1 - 2 is negative, but can you see that 6? And actually that even exponent, I was gonna even say here, doesn't really matter what I substitute instead of x. I will always have positive because I will take the power of 6. Taking a value to the power of even number, it's always an even number, right? That means this is positive and this is also positive. 14 times 1, it's also positive. That means I do have positive. Can you see? At 2, first derivative is not changing the sign. Okay? I will draw it later, but function is like increasing and then again is increasing. Yeah, we do not have local extreme values. Okay, but let's keep working. -1. If I substitute -1, -1, -1, -1, we know that these terms, x - 2 to the power of 6, x + 2 to the power of 6, they always positive. That means I can focus just on 14 times x. 14 times -1, of course, is negative number. Okay, and then let's test another interval, -3. If I put -3, -3, -3, I'm not testing this because it's positive. 14 times -3 is again negative. Okay, that means now my function behaves like that. Decreasing, decreasing, and then increasing, increasing. Yeah, that's my symbols. And we can see function is decreasing and then increasing only at 0. At 0, we're gonna have local minimum value. Right? Local minimum, just at 0. At -2 and at 2, no. Because function is like decreasing, decreasing, increasing, increasing. Right? I can possibly guess it's decreasing and then something like that. We do have horizontal, and then again, that means we have to have some indication of that the first derivative is, oh, my graph is a little bit slopey. That means that will be 0, and this will be corresponding values for 2 and negative. That's possibly the graph of the function. Okay, but we can see now we have horizontal tangent, but derivative is not changing the sign. I can remove it because it looks funny. But that's the shape of the function. I can even see based on that. Okay, that please remember. And one thing that you may notice, that's what I said. Then we can see at -2 and at 2, we don't have critical points. And you can see -2 and +2 came from that even, like a multiplicity, like the even power. Always when the factor is taken to the power of even number, we're getting that 0, we're getting that critical number, but derivative, that function derivative will not change the sign. Will be either negative, negative on both sides or positive, positive. That means even looking at this, I could tell right away that at 2, at -2, no local extreme values because of that 6. If this will be 2, 4, 6, 8, any even number, no changing the sign. X is just X, just 0, one positive value. Just one single value, which of course, if it's negative, it's negative. If it's positive, it's positive. It's changing the sign. Okay, that's when we do have only local minimum at 0, because that was the confusion. No local extreme values at -2 and +2. Okay, and let's do the other one. Let me check, because I will switch the slide, but I have the list of the functions somewhere. Okay, that's me. Let's do 19. Question 19 is a function of x over x squared plus 1. Okay, rational function. We have to look at the denominator first in order to determine the domain, but this is not -1, it's x squared plus 1. That means I can accept any numbers. Denominator will be never 0. Okay, that means all of the numbers, good. I don't have to exclude anything. And let's try to find the derivative first. We have to use the quotient rule. Derivative of x is 1 times denominator minus x times derivative of the denominator 2x, and x squared plus 1 squared. Yes, we remember the quotient rule. Let's simplify. X squared plus 1 minus 2x squared, and then x squared plus 1, and again squared. One more time. 2x squared, negative 2x squared plus 1x squared is just this. Okay, and now having this form, I have to find a critical points. That means derivative is 0 if and only if numerator is 0. Okay, that means only if I'm looking, this is my derivative. Okay, that means derivative is 0 if numerator is 0. Because fraction is 0 if the numerator is 0. I can't have 0 in the denominator. And then I have 1 minus x, 1 plus x. And this is giving me 1 single number. We can see no powers. And this will give me -1. And both of them are in the domain. That's my critical numbers. Okay, but we also have to find out the values that derivative is undefined. Okay? Derivative is undefined if denominator, like fraction is undefined if the denominator is 0. If the denominator is 0. And my denominator is x squared plus 1, squared is 0. Quantity squared is 0 if just the quantity is 0, but we can see x squared plus 1 I can't factor out, or I can say this way, quantity squared is never -1. We have no solution. No solutions. And that means no critical value. But we may have the values from that. Please remember. Okay, that means I have 1 and -1. And now, which one is giving me maximum, which one is giving me minimum? Let's put them on the number line, -1 and +1. And I will be testing a first derivative. And the best one is actually this one. Oh, that's my nice formula. And I'm testing the sign. Let's do the same. Test values. Let's put 2. If I will put 2 instead of x, 2 squared is, okay, I don't want to mess up. Oh, I am messing up. You can maybe, because I'm not asking you a questions. Okay, if we put 2 instead of x, we have 2 squared, 4, 1 minus 4 is negative. And also, I don't have to be worried for the denominator because it's squared. It's simply positive. That means this will give me negative number, this will give me positive, this will give me negative. But we know that I am testing this. If I put 0, I have 1 minus 0, positive. If I put -2, I will have the same situation like +2. Okay? Because we know they not always alternate. No. Okay, and then the function behaves like that. Decreasing, increasing, decreasing. Decreasing and then increasing, attaining local minimum, and then increasing and decreasing local maximum. We can see how nice we can read this. local minimum at -1, local max. That means at -1, we have local minimum, at 1, we have local maximum. We can see from the graph. Okay, good. Do you have some questions? Okay, I will ask you a question. Let's keep moving. What else we have? Okay, somebody asked, is the same section and it's just question 21. That means the same idea, and somebody asked for this question. That means I will solve this one. We have, again, nice function, just the polynomial, domain are all of the numbers. But what we have to be really careful. Let me write x cubed times this. That means we have to use the product rule. Let's use it. Derivative of x cubed, 3x squared, times this, plus x cubed times derivative of the second part. We have quantity to the power of 4. This will be 4 times this quantity to the power of 3, and times -1, which is the derivative of the inner function, chain rule. Oh, let's make a nice, let's clear this. Let's simplify. I will copy this, and then I have negative, actually, 4x cubed and 1 minus x cubed. So I see two terms, and I see x squared is a common factor. I can factor out, and 1 minus x to the power of 3. So I will factor out, because otherwise I will not see the product. I mean critical points. I will factor out in front of the parentheses x squared and 1 minus x cubed. And what's stay? 3 stay. Yes, looking at the first term, maybe I can just indicate the terms. This and this. That's me looking at the first term. I took away x squared, and I took away 1 minus x cubed only. That means 1 minus x to the power of 1 stays, and 3. Minus. Looking at this, I didn't take away 4. I took away from x cubed just x squared. That means x stays. And I took away everything of that 1 minus x cubed. Okay. It means my first derivative looks like that. X squared, 1 minus x cubed, and this will be 3 minus 3x, 3 minus 3x minus 4x, 3 minus 7x. Really nice product form. That means that's my derivative. Okay, and who can tell me the critical points? Because derivative is 0 if this is 0, right? That we have, what critical points we have? From here, and from here. Do you think you can tell me? This will give me what? In order to get 0, it's just 0. Thank you, 0. What about the second factor? What value will give me 0? What I have to substitute instead of x? Oh, 1. Thank you, Craig. Thank you, Craig. Ryan, thank you. And this one? What I have to substitute instead of x? Actually, 3 minus 7x must be 0. We can subtract 3, and we can divide by -7. 3 over 7. Okay, that means that's just the solution of the linear equation. Okay, that we do have 3 critical points. And what do you think? At which one? We still don't know minimum, maximum, but at which of those, 0, 1, or 3 over 7, which one will not give me local extreme values? Which one will not give me? You remember I told you that x, yes, 0. Thank you, Ryan. At 0, the first derivative will not change the sign, because it came from the square, from the multiple. Okay, that means That's the thing. We can, I don't have, oh, I will try to test it. Oh, my internet is again slow. I don't know why. I think it's not my internet, it's my laptop. No, okay, I'm writing. That we do have 0, 1. Oh, no, 3/7 is small. 3/7 and 1. No, don't do this for me. Okay. And that's my first derivative, and I'm gonna test. That means I will substitute 2. Oh, that's tiny. Okay, 1/2. Oh, that's tiny intervals, right? Extremely tiny. What's the number between? Maybe 1/4. 1/4. Okay, that means I'm gonna substitute all of these values. If I substitute 2, I will have negative, negative, and positive. 2 negatives will giving me positive. If I substitute half, half will give me, of course, positive. 1 minus half is positive, but half, 7/2, is giving me, that means this is positive, positive, negative. This will give me negative. And if I substitute 1/4, positive, positive, and 7, oh, no, why can't, 7, because we have to change the sign, correct? Okay, what's happened if I substitute 1/2? Oh, hang on. I have a question from Ryan. If you have a positive exponent, it will not give you a change of sign. Oh, no, Ryan, not positive exponent, even exponent, because each exponent is positive. 2, 3, 4, 5, 6, 7, even exponent. Okay? Ryan, I'm just trying to read your question because I just realized now. Yes, that's me, not yet. That's okay, that's correct. Even exponent. Okay, but we really have to, because we know, yeah, do you see what I'm doing? Because I'm doing my arithmetic, and we can always make some mistakes doing the arithmetic. The thing is, we know that at 0, we're not changing the sign. But at 1 and at 3/7, we have to. 1/2 is definitely greater than 3/7, and 1/4 is definitely lower. Am I right? But I can even pick tinier number, like let's say 1/100, small number. If I will put 1/100, that's positive, and this will be positive. That means this is definitely positive. Okay, works. And we can try, let's put like negative, tiny. Oh, actually, we can put huge, like negative, we can put -1. This will give me positive, but this will be -7 times -1. It's +7 plus 3, positive number. That we can see at 0, we're not changing the sign. And how function behaves? First derivative test, increasing, and then decreasing, increasing. And we can see local maximum, local minimum. That means this is max, and this is, of course, minimum. It means at 3/7, local maximum value, at 1, local minimum. Okay. I think I was okay with my arithmetic. I was just worried for these numbers. And this weird symbols, that's actually first derivative test. Yeah, how easy and simple it is. Okay, let's see what else you asked me on the discussion board. From section 4.2, where is my list? You ask question 16 and 17. which is similar. Let's do maybe one of them. It's the same thing. Okay, that's me. Hang on, we have to add the inflection points. That's me. Let's do 16 first. I can maybe do just 16. Okay, we can see domain, all of the numbers, no problem. We need the derivative, 4x cubed minus 4x. Derivative is 0 if and only if 4x cubed minus 4x is 0. Let's factor out 4x. And let's factor out x squared minus 1, x minus 1, x plus 1. This is giving me, can you tell me the critical points? Who can tell me the critical points? The first one, the second one, and the third one. Can you type for me? Critical numbers. 0 for this, great. The second one, 1, excellent, and -1. Thank you. See how nice? And now let's look at the final form of my derivative. This is my final form, and I will test it in a minute. But do you think at each of them we will have local extreme values? At 0, at 1, at -1? You can see none of them is, yes, thank you, Andre. Of course, derivative will change the sign, simply. This is -1, 0, 1, and we testing that box. That's my derivative. If I substitute 2, I have positive, negative, positive, negative. Because if you confident with one of the sign, then we can alternate because we know that we have to change the sign. Okay, and then function is decreasing, increasing, decreasing, increasing. Local min, local max, local min. At -1 and at +1, function has local minimum value, and at 0, local maximum value. Nice and easy to recognize. But, however, what we have to do, inflection points. That means for the inflection points, let's find the second derivative. I will use that form because it's much, much easier to find the second derivative. 12x squared minus 4. Now, second derivative is 0. If this expression is 0, I can factor out 4. 3x squared minus 1. Okay, and I can write square root of 3x minus 1 and square root of 3x plus 1. Yeah, just the weird numbers. Because I have to take it's not a perfect square. That means I have to keep the perfect square. I have the room actually. Let me write one more time. Second derivative is 0 if 12x squared minus 4 is 0. That's the right. Factoring out 4, we have this, and then square root of 3x minus 1, square root of 3x plus 1. And then this will give me 1 over root 3, and this will give me -1 over root 3. And 4 is not giving me anything. That means this is my second derivative. And since the same idea, none of the product were taken to the power of even number, at both of them, we will have inflection point. Let's put them on the number line, and let's test the second derivative. I think, 2AV, this is the good thing. Second derivative, and we're changing the sign. That means the signs will alternate. This will give me positive, negative, positive. Because you can even see that's the second derivative. Maybe even this one is nice form. It's quadratic function with the leading coefficient positive. That means it's just open up, and we know the zeros. Okay, that's my second derivative. -1 over square root of 3, +1 over square root of 3. And this part is above, positive. This part is above, positive. This one is negative. That means you can also draw a function. We not always know the graph, but if it's quadratic, it's perfect. This should be exactly in the middle, -4. Okay? But we can also test. Okay, that means function is concave up, concave down, concave up. It's definitely changing sign at these numbers. That means both of them are the inflection point. Okay? At that point and at this one, function has inflection point. Inflection point. Huh? Not working. Oh, no. Okay, inflection points. Okay, that means that's how we can test. That's how we can test for the inflection points. Okay, let's see what else, because I do have from section 4.3, that's from 4.3. You asked me question 29. Oh, let's do 29 and let's do 31. Okay. Oh, we did 31. Oh, hang on. This is a global. Okay, that means we will use maybe the information that we just did, because somebody asked for this question, 29 and 31. Okay, that means now global maximum. We have to find the highest point on the graph and the lowest point on the graph. Okay, that means we will try to look at this. And let's see, 29. G at t is defined as a t e to the negative t. And we know that we can only take values, that's my domain, greater than 0. Okay? We're not even including 0. That means probably we're not gonna have one of the ends, but we will see. And what we will do, let's start with the critical points. Because since domain, that's the thing, right? Since domain is not defined as a closed interval, we don't have really the values at the endpoints, because 0 is not included, and then infinity, that's because t goes from 0 to infinity. That means I don't know exactly the situation at the endpoints, especially at infinity, right? But we can try to figure out. First of all, I will find the derivative, because I really like to see my critical points. They will tell me something. Okay, product rule, I will put the dot. Derivative of t is 1 times e to the negative t plus t, and derivative of e to the negative t is e to the negative t times -1. Let's clear things. E to the t plus, actually minus -1 times t and this. And we can try to find the t value that derivative is 0. I can factor out e to the t. Okay, and then I have to say e to the t is 0, or 1 minus t is 0. 1 minus t is 0, of course t is 1. Do you think e to the power of t, do we have a situation that this will be 0? Like e to the power of any number is never 0. That we have no solution on this side. Okay, that means 1 is greater than 0, is in the domain. This is the only critical point. Let's test it. I will put t, I will put g prime, and I am testing 1. And which formula I will test? I believe this one is good. That's G prime. If I will put 2, 1 minus 2 is negative because e to the t is always positive. And if I will put 0 or 1/2, 1 minus 1/2 is positive. Okay, that means I can see that function G, it's like increasing and then is decreasing. We do have local max at x1. Okay, and we see a little bit the shape of the function. Yeah, probably it's not just the parabola, but that's what we can say. What do you think? It's also one highest point, the global maximum. How do I know? What do you think? You can see that we still don't know concavity, right? We don't know how the function is bended. Probably it's bended down like that, but we can see this is the only has to have the endpoint. I know that we can see function is going from the below and it's going down at the end of the domain. That's because I can maybe add 0. That's my 0. Okay, that's we can see, and it's actually because this is above, right? Because it's positive. Okay, I will remove this because it's just the test. Oh, I can write it this way. Oh, that's better. And this is 1. Okay, that's better because the values are definitely positive. We can see if I substitute 1, I have e to the power of -1. That means this value, actually, we never computed, but it's 1 over e. Yeah, that's the reason that I wanted. But you can see, yeah, we can definitely, yes, the local maximum would be the global, yeah, correct. Because how do we know for sure that I don't have any highest point? Because this is the only interval that function is increasing, attaining this maximum, and then decreasing. We don't have, again, the situation that function is going up. Yeah, that's the only intervals for the monotonic, increasing, decreasing. That means this must be the global maximum. And we can base on this one. And no global minimum, because I can't detect function is going down and I don't know. Or maybe not so much, because we have to be careful with this, right? Because I don't think function will be, for the big numbers, will be just above, but that's okay. We don't have to know. We have to determine the global maximum minimum. That we can see the global max, it's definitely at x equals to 1. At x1. And I even compute this because if you, global maximum will be the value of the function at 1. 1 e to the -1. 1 over e. That's what I put. I just use the original function. Okay? And no global minimum value. We can't detect the lowest point since we don't really have domains. Domain is not a closed interval. Okay? That means that's how we can deal with this. And actually 31, let's try. I will try to come back. Do you remember that function? Oh, it's the same function? I think it is. It's just x. That means, what do you think? This is the same function like 31, but now we're not only asking for the local extreme values. We're asking you to find the global. Oh. And you can see we almost have the graph. That means, what do you, and domain is all of the numbers. Okay, and they didn't give us, you see, they didn't give us any restriction of that. That means I'm assuming that my function is defined everywhere. Everywhere means this, right? I see the answer, Ryan. No global values. Let's come back. Okay, can you see? The function will be like that. I don't wanna, the function is going up on this side and it's going down. That's we don't have highest and the lowest point. I will remove that. We can see even on this first derivative test, we can nicely see the shape of the function. Probably inflection point somewhere here, but that wasn't the question. And we can see no global values. Okay, no global max or min. Okay, good. Oh wow, that's yeah, we talking a lot about this, but that's important. And then I think I have last question, this one from the discussion board. Okay? That means this is kind of like we call optimization problems. It's the same thing, it's the word problem, but the point is to find the maximum or minimum, depends what they're asking. That means let's try to solve it. A rectangular swimming pool is to be built with an area of 1,800 square feet. Okay, rectangular. Okay, that means we have a rectangular and we can say A and B, right? And I can say right away that A times B, it's 1,800. Okay, I did translate my first sentence. The owner wants 5-foot wide deck along either side and 10-foot wide deck at the two ends. Okay, that means he wants 5 and 10. Okay, that means this is 10 at the ends, and this is 5. Okay, cool. Find the dimension of the smallest piece of property on which the pool can be built, satisfying these conditions. Find the dimension of the smallest piece, because that means we have to maximize. Do we have to maximize this swimming pool? Find the dimension of the smallest piece of property. Okay, that's no, we have to minimize. I'm just confused with the question. Maybe you can help me. I was looking at this question, of course, before. Find the dimension of the smallest piece of the property on which the pool can be built. Let's do it, because first of all we have to create a few functions, because I'm just don't like this word smallest, because what we have to do, based on the smallest piece of property, we have the property, like he has the property of 1,800 square feet. Find the dimension of the smallest piece of property in which the pool can be built satisfying this condition. Okay, I'm assuming that he wants in that 1,800 square foot with this 5, 5, 10, 10 decks around, he wants to squeeze this. That means this has to be like, we have to find out the dimension of this. We don't have to be worried. That's what I will do. I will try to find out, because the area, we have to look at the area of this pool. Okay? That means the area of this pool. Oh, hang on, Ryan. The rectangular swimming pool is to be, okay. Thank you. Now I think makes sense. Oh, wow. Am I crazy? Of course it says the rectangular swimming pool. Am I? That means this is A and this is B. Okay. Let me do this. Thank you for, oh no, it's not 18,000, it's 1,800. Okay, that means 8. Oh, okay, now I understand. Now, okay, the rectangular swimming pool is to be built with that means the swimming pool must have 1,800 square feet. Okay. He wants the deck to increase and be, okay, that means he's looking for the big rectangle that I draw has to be like minimum. We have to minimize because that's the area of this property. That means, let's see. now let's name this distance. For now, I will name, this distance will be A plus 5 plus 5, because we can see it's A and then 5 and 5. This distance is B plus this B plus 10 and 10. I can say 20 right away. And I can say 10. Okay, that means that area, A plus 10, B plus 20, we have to minimize this, okay, because we have to find the dimension of the smallest piece of property, and that's the property. Okay, and we can see that's what I was saying. We trying to have a function and trying to minimize this function. In order to minimize, we have to find the derivative, critical points, and minimum. Okay? We do have some restriction, of course. I mean, A could be any number. A and B could be any positive number, with the product being 1800, of course, but that's not the any number. We may have it. Okay, that means now what I will do. From this, I will solve this equation for B. B is defined 1800 over A. Okay? And I will substitute to this. First of all, let me, I can actually keep the product. 10, A plus 10, and then B is 800 over A plus 20. Because what I have to have a function which depends on one variable, A. Let's distribute everything now. Let's FOIL. I will multiply this times this, and I will multiply this times this. A times 1800 over A is just 1800. A times 20 is 20A. And then 10 times 1800 is 18,000 over A. 10 times 20, 200. Okay, that means that's my function, which represents that piece of property, the area. Now, let's find the derivative. And we can see all of the numbers, we don't have any restriction. That we have to find the local minimum value, and this will give me the answer. This will be the lowest value, will give me the smallest piece of property. Okay, 1800 will give me 0. Derivative of 20A is 20. Derivative of 1 over A is negative 1 over A squared, but I will copy a constant. And then 200 is 0. Okay, that means derivative A prime is 0 if this is 0. Oh. I can divide both sides by 10. Then I can lose 1, 0. And then I have, what I can do. Okay, let me do this way. 1800 over A squared minus 2. And I can cross multiply. 2A squared is 1800. I can maybe move my solution here. Then A squared is 900. And A is square root of this, which is 30. We have to skip the negative in this case. Or I can write right away, A is 30. Okay, that means probably 30 feet. I just need room. But let's check what is happening. A, it's 30, and let's check the sign of the derivative. That's what we were doing. And where is my derivative? Okay, I believe this one will be good for me. Okay, if I will put 1, for example, the value 1, because I can pick any test value. 1 will give me 20 minus 1800, of course, negative. And if I will put huge number, then this is small, right? This will be small, and then 20 minus the small number is positive. Okay, that means function, which is my area, it's decreasing and then increasing. We will have local minimum value, but we agree that this is the lowest value since the domain is not bounded. Okay? That means the answer is dimension. That means we need A and we need B. Oh, no, 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 no. Let me put this. We need length and width. Length and width. And who can tell me the final answer? That's width and that's length. Right? That means width is A plus 10, which will be 40. And length is B plus 20. B, we can compute maybe on this side. B length is B plus 20. That's the dimension of the property. B is 1800 over A, which A we've got 30 plus 20. We can drop zeros. 18 divided by 3, it's 6, 60 plus 20. The length is simply 80. Okay, that means 80 by 40 will give me the smallest piece of property. And thank you, who correct me, Ryan, thank you for helping me with the original settings, the first sentence. Okay, but we can see the idea is, yeah, thank you. Because otherwise, wow, if I will put the other dimension, that's, but you see, even if that actually was, I know, the mistake, but even the mistake that I did, this word didn't make sense for me. That means I didn't keep working and I didn't like spend time. This word right away like was weird. Like I said, how he wants to minimize, smallest minimize if he has the dimension, but of course that was the swimming pool. Yeah, that's mean always when you make some mistake, wrong assumption, you can figure out that something is wrong, which of course you help me because you watching me doing this. But that's also nice, and we call optimization problems. Okay. Oh my gosh, the session is too long, but we will probably finish the session. But let me see what I have, because that's all of the questions from the discussion board, which I'm so happy that you asked, and I'm so happy to help you. But let's see what I have for you, okay? Okay, that's the same question actually. I have extra slide. That's different, but we will skip this question. And then what I've prepared like, the same concept, but different functions. That means maybe I can skip this because we know how to find the local minimum maximum, okay? Because of the previous questions we did. That means I can type the solution or write the solution for you, and this will be on the PDF format of my session, okay? That means we will skip this. You can try to solve it, but I will type the solution later. I have another one, which actually we did similar. I have another one, trigonometric. Maybe we can try to solve this one. Let's solve this one. Critical points and inflection, the same thing. The only thing what I will do, since it's trigonometric function, periodic function, I will set up the domain from 0 to 2 pi. Because we know every sign will repeat every 2 pi. Okay, let's find the first derivative. Derivative of x is 1. Who can tell me derivative of sine of x? Derivative of sine of x? Cosine of x. Thank you. Okay, and now for the critical points, yes. Derivative must be 0 if cosine of x plus 1 is 0. Then cosine of x is -1. Do you remember once I gave you the values? I don't know if we remember, that means cosine for what angle is -1? I can draw cosine curve because it's worth to know the cosine, and that's pi over 2, that's 3 pi over 2, that's pi, and that's 2 pi. That means we can see 1, -1. That means cosine is -1 at pi. Okay, pi is the critical point. I can put this on the number line, and I can try to test the sign. This is a little bit, yes, a little bit challenge because of the trigonometry. But let's see. pi, if I will put, that's the only critical point. If I will try to find out what is going on with cosine, but I have to find the values. Okay, let me put the test values. That's probably a little bit challenge if we don't know. Let's put pi over 2 and 3 pi over 2 because we know the values. If I will put 3 pi over 2, cosine at 3 pi over 2, we can see is 0. 1 plus 0, it's positive. Okay, not bad. If I will put, it's again 0. Because everything is positive. Am I right? If I will put pi over 2, cosine at pi over 2 is 0, 1 plus 0. That we can see for the trigonometric, even if it's not taken to the power of even or number, we also can't assume. Since derivative is not changing the sign, we don't have local extreme values. Function is increasing and increasing. I can possibly draw this function cosine of x plus 1 because this was just cosine. Because we will even need, I have to take this function and lift 1 unit up. Okay, that means I will have this a little bit bigger. Oh, that means now this is pi over 2, 1, 2. This is 3 pi over 2, and that's 2 pi. And actually we can see, doesn't really matter what I substitute instead of x, the first derivative, because this is first derivative, 1 plus cosine of x. I shift cosine of x, 1. It's always positive. If the first derivative is always positive, function is always increasing. Okay? We still don't know how this function looks like, right? Because this is just the derivative. And now we can try to, we know that it's just always increasing. No local extreme values. Let's try to find the second derivative. Second derivative will be just the derivative of cosine. Who can tell me derivative of cosine before the midterm? Helpful question. Negative sine of x. Thank you. Okay. And now, in order to find a potential inflection point, the second derivative must be 0. Which means negative sine of x must be 0. And when like for what angle sine of x is 0? Oh, lots of trigonometric functions today. Sine looks like that. Or I can even draw negative. Negative is flipping everything like a mirror image. That means this graph is negative sine of x. 2 pi, pi, and 0. That we can see 0, pi, and 2 pi, if I include the endpoints. That means that's potential inflection points, but I will not include the endpoints because we can, if I will test, because I don't know what is going on the other side. That means I will only take pi. The easiest way is to have open domain. Okay, that means we're not including the endpoints. That means if this is pi, we can actually we have the graph, the green graph. That's the graph of the second derivative. If x is pi, second derivative is below negative on the left-hand side, and it's above positive on the right-hand side. Okay? Then this means function is concave down and concave up. We do have inflection point at pi. That means no local extreme values. This is still critical point, which actually the question is asking for the critical point. I was so focused on the minimum maximum. That means this is critical point. Critical point. Pi, and the same thing, coincident, inflection point also at pi. Okay, a little bit of trick. Let me check, because I know that I'm keeping you too long. I didn't expect the session to be too long, because you know, if we would like to solve all of my questions that I have, probably we need another hour, but no, we will not do it. Okay, I have this question. Okay, let's do it. Because I don't want you to miss the questions on the test, and of course on the any quiz, any test, any midterm final. Okay, let's see, maybe we can find. We have 5 functions, and based on this description, maybe you can tell me, maybe this question is like 2 minutes question. Based on this description, we have to pick which one corresponds, which graph corresponds to this description. First of all, we see derivative is 0 at 2. What this means, that derivative is 0 at 2. Horizontal tangent, 2. Oh, horizontal tangent. Horizontal tangent. Thank you. Yes, and even here, horizontal tangent. Even here, horizontal tangent. Oh, wow. I can't exclude. Each of them satisfied this. Okay, I can say horizontal. You can think about the rest, and I will write horizontal tangent at 2. Okay, now, second derivative is less than 0 for all of the values of x less than 2. That means, if the second derivative is negative, what's the position of the function? I mean, what's the shape? What's the shape of the function is? If the second derivative is negative, do you remember? Yes, concave down. Thank you. I was writing my symbols. Concave down for all of the x's before 2. That means, let's see. Concave. Oh, is this concave down? Not really. No. Oh, is this concave down? Yes. Oh, that's not. Oh, we can see we have concave up, concave down, too much. And this one is also good. Okay, I did eliminate 1, 3, and 4. And now concave up, right? Concave up. For all of the x's, for all x's greater than 2. That means which one? 2 of 5, of course, it's concave up. This is the correct answer. And you can say, that's how you can analyze the graph, how the derivative affects the graph. Good. We will skip this one. We will skip this one. We did this one. For the function, okay, we can skip this one. We can skip this one. You have the solution. Oh, actually. Oh, I would like to solve this one. Let me check. We will solve this one, and then we will solve one question from this section, okay? And we will be done, I promise. I promise. I know you really patient. Okay, because this is typical question to find the global maximum minimum, having a function and having a closed interval. That's what we didn't have before. Because what we have to know, first of all, normally I will write that the domain is all of the numbers, polynomial, but now not really. Oh, somebody asks, so you will have both the global max? Yes, exactly, Raya. If the function is defined, if function is actually continuous function, if we have continuity, and if the function is defined on the closed interval, always global max and min exist. Okay, that means let's see what we have to do. We have to take this function and find just the value at the endpoint, at endpoints, at 1, at the negative 1. But also, I have to find the critical points. I don't know how many of these critical points I have. And I also have to find a corresponding value. And whichever is higher, global max, whichever is lower, global min. Okay, first of all, let's find the critical points. I need derivative. 3x cubed, it's 9x squared minus 24x, that's it. I can factor out 3x minus 8 equals to 0. X is 0, or x is 8 over 3. But what is also important, we really have to check 0, it's actually in the domain, fine. But 8 over 3 is greater than 1. That means I don't have to take this, because that's the common mistake. We know this is the critical point, but if I will take all of the numbers, it's not a critical point when I have limitation. That means the only number that I will test is 0. I don't have to test this one because it's outside my interval. Okay, now watch me because I will do the arithmetic. We have to substitute -1, -1. -3 minus 12 plus 1. Am I right? And this is -14. Okay, now let's substitute 1. 1, 1. 3 minus 12 plus 1. -8. And substituting 0, we're just getting 0, 0, 1. Okay, that we can see this is the highest point. That means that's global max, and this is the lowest point, if we will draw it. Global minimum value. -8 is just like another, I mean, it's just the endpoint. Just the endpoint. I don't know the graph exactly, but what we have at -1, oh, -14. At 1, -8, and at 0, it's too tight. Why I'm just trying to, let's make wider. -1, it's -14. At 0, we have 1. And at 1, we have this. That means probably, I don't know, actually. I don't know exactly. But we can see this will be the highest point. And we're only looking from -1. We go -14, okay, lowest point. That's -8, just the end point. And 1, that means this is max, G, global. And this is mean. Okay, that means that's the typical. Yeah, please remember, if you have a closed interval and continuity, you will always have highest point and the lowest point. Okay. Oh, I wanted to finish. No, just one more thing. Profit, cost, and revenue. That means let's just see, we have to know this. Okay. That means the maximum profit can happen when marginal revenue is the same like marginal cost. And we remember, the marginal revenue and the marginal cost are simply the derivatives. That means looking at the graphs, we can say that the slope, at some point, if the slope of the revenue function and the cost function is the same, then we do have a maximized profit. And we can see slope of this line is actually constant, but if I will draw the tangent line at the point Q2, Q sub 2 and Q sub 1, I do have the same slopes of the function C and R. That means if you can find slope means derivative at this point, slope of the tangent, slope of the curve. That means if you have the same, okay, the same slope, this means that we're maximizing profit. Okay? Both of them. Okay, and then I have one question. The figure below shows the graph of the cost function, Cx, C of x, and the linear revenue function, R of x. Choose the correct statement. That means everything, the statements that I create is at the point D. Okay, that means you can probably guess that the slope at D is the same like slope here. That means, what do you think? Which statement is correct? At D, marginal revenue appears to equal marginal cost. Profit is maximized. Do you think it's just this one, correct? Marginal revenue, okay, marginal revenue equals to the marginal cost, right? Which means profit is maximized. I think, yes, this is the correct statement. And you can, yes, you can look at different, yes, you can look at different statements. The marginal cost is negative. No. Negative means that the line will go down. Nothing is going down. Wrong. The cost